So today we are going to analyze randomized quick sort. So we have already seen how normal conventional quick sort algorithm works and what are the different cases of time complexity, like in case of average case how it behaves, in case of worst case how it behaves, in case of best case scenario how quick sort algorithm changes, and what are the related to that. We have also seen how this imbalance partitioning actually increase the time complexity, and I mean increase the time complexity like theta of n square, and how balance partitioning provides better time complexity. And also we have seen that in average case time complexity of quick sort is O of n log n. Before that, you have to understand how randomized quick sort works. So randomized quick sort, actually one changes happens, that is we choose the pivot element randomly, and in case of conventional quick sort algorithm we have seen here that the last element being chosen as a pivot element. So last element, which is here this 4, has been chosen as a pivot element in the algorithm itself. So if you see the algorithm that AR equal to X, so that is the pivot we have chosen. In fact, any pivot element we can choose, and in case of conventional quick sort algorithm, the partitioning method and all, you have seen how actually the element which are less than the pivot element comes under this tan value in array P to I, and the blue values in array I plus 1 to j plus 1, having those values which are greater than or equal to the pivot element X, and all I mean the wide value portion, wide values, that is a j to r minus 1, this is r which is pivot, this is r minus 1, and these have unknown relationships, so we don't know how this part of the array and what are the relationships with the pivot element, that we don't know. So these things we have discussed, and how partitioning algorithms happens we discuss. And also you have seen this imbalance partitioning and then balance partitioning, these are all things we have checked. Now we are going to discuss this randomized quick sort. So randomized quick sort, only one thing, that is that in case of conventional quick sort we checked this last element as a pivot, but here we will be using the random function, and we'll have some value, randomly chosen value, and that will be exchanged with the AR, that will be the pivot element, and remaining partitionings will remain same like conventional quick sort only. So we'll call it random partitioning, and we'll call it randomized quick sort. So main changes that is happening is the selection of the pivot element in random fashion. That means where this probability comes actually. So the changes that are happening in randomized quick sort is partition and the quick sort. I mean these are very small amount of changes are happening. The new partitioning procedure will be called randomized partitioning, simply swaps before performing the partitions, and the new quick sort procedure, randomized quick sort, calls the randomized partition instead of partition. So these are the changes that we are looking for. And how we can analyze in case of worst case scenario. In case of worst case scenario, the worst case time complexity of quick sort is Tn equal to maximum of Tq plus Tn minus 1 minus q, and this is theta n. So theta n is nothing but, so what is theta n? Theta n is represents the time complexity of the partitioning step. That means every time you partition one element you pick for the partition, that is having 1, O1. So for n number of element, if they are participating in the partitioning technique, that will be theta n. So that this theta n is for that purpose only. Every time you break into two sub-arrays, that partitioning method, for one element it is 1, O of 1 or theta of 1, and for n element it is theta n. But then once you break it, then we have the two subarrays. One subarray we call TQ and another subarray we call Tn-1 minus Q. Okay. So what is this? The Q represents the size of one of the subproblems resulting from the partitioning steps. It varies from 0 to n-1, where n is the size of the input array. Okay. So the recurrence relation TQ represents the worst case time complexity for a subproblem of size Q, and remaining Tn-1 minus Q represent the worst case time complexity for the complementary subproblem. That means once you divide it, it gets partitioned into two parts. First part we'll call TQ and second part we'll call Tn-1 minus Q. That's why it is like this. Whichever is the maximum, whichever consume the maximum time, that will be the worst case time complexity. And this is nothing but Tn will be equal to big O of n square. This we can do very well by guessing method, using that capital T is not less than, it is less than C into n square. And if you substitute this, if you substitute like this, Tn equal to C n square, you will end up getting O of n square. Okay, so this is the worst case analysis of quick sort. So this analysis of worst case analysis is same for both quick sort or randomized quick sort. There is no change. Okay, so worst case analysis will be big O of n square. So next is expected running time. What is the expected running time? What is the expected running time of randomized quick sort? Expected running time of randomized quick sort is big O of n log n. So the expected running time of quick sort algorithm is big O of, randomized quick sort is big O of n log n. That we are going to prove today. And running time and comparison, quick sort and randomized quick sort differ only in pivot selection, sharing the same procedure otherwise. Randomized quick sort running runtime is analyzed by considering quick sort and partition, assuming random pivot selection by randomized partition. The running time of quick sort of an n element array is big O of n plus x, where x is the number of element comparison performed. So lemma 7.5, what is the summary? Summary is that quick sort runtime is big O of n plus x, or x denoting the number of comparisons. Partition dominates the quick sort runtime. Each partition call contributes O1 time, as I mentioned earlier, plus the proportional to the comparisons, leading to the total runtime O n plus x. Now here we have to determine Ex, which is the expected total comparison, by understanding when elements are compared, indexed by their positions in sorted array. So expected running time, we have expected time complexity, actually expected running time, that we have to calculate. Now what is expected runtime or expectation in probability theory? So expected value in general, the value that is most likely that the results of the next repeated trial of a statistical experiment, that is called expected value. So you have to find their expected running time. So the probability of all possible outcomes is factored into the calculation for expected value in order to determine the expected outcome in a random trial of an experiment. So therefrom this expected value comes. It is coming from the probability theory. So expected value uses all possible outcomes. That means this quick sort algorithm, when we are considering the randomized quick sort, you have to take many trials. So what is the formula? The formula is Ex, which is the expected value, is equal to n equal to 1 to n and xi into pxi. Pxi is the probability. So you can see here, when the experiment involves numerical data, the expected value is found by calculating the weighted value from the data using the formula Ex equal to xi into pxi, and it has summation 1 to n. So an example if you take means you will understand. For example, a game is created where the rolled number on a single die is the amount paid to the player in dollars. The outcomes of the roll of the die will be the number 1, from number 1 through 6. The probability of each value is 1 by 6. So each 6 outcomes are having the same probability 1 by 6, which is a die. Since each value is equally likely to be rolled, so here one table you have taken. So this is roll X. These are the events. Six times you have rolled it, and probability of rolling is 1 6 1 6 1 6, equal probability. Any phase can come, I mean, because we are rolling the die, and the amount is given is this. These are the amount given for each occurrence of the event. Okay, so these are the occurrence. So finally, how the expected value will be calculated? So I equal to 1 to 6 xi into pxi. So first occurrence, this is amount is 1 and probability is 1 by 6. Second occurrence, amount is 2, probability 1 by 6, like that. This all has to be multiplied and then added, and then finally you will get $3.50. This is the expected value. So this is how it, so that means probability of roll into amount given, that means px xi into pxi. This is what we have to do for all occurrences. Okay, that is how we should calculate the expected value. Now let us come to the quick sort algorithm. Now let us come to the randomized quick sort. So here what it is that so this is the first lemma, which is lemma 7.1, which says that the running time of quick sort of an n element array is big O of n plus x, where x is the number of element comparisons performed. That is fine, and then we have to calculate the ex. Next lemma says that during the execution of randomized quick sort on an array of n distinct element, which is z1 to zn. Okay, so this z1 to zn is in, let's say, ascending order. Okay, z1 to zn is in ascending order. So here z1 to zn, n distinct elements are there. So z1 to zn is the ascending order elements are there. See that z1 is less than z2 and z2 is less than z3. Okay, so in randomized quick sort on an array of n distinct elements, z1 less than z2 less than zn, an element zi is compared with an element zj. What they are trying to say is that zi is the ith smallest element and zj is the jth smallest element. Okay, so these two will be compared, which is true, because at the end almost all the element of a randomized quick sort will be they will be participating in the as a pivot or during the execution of randomized quick sort of an array of n distinct element, and these elements have been taken in such that they are in sorted order. That means z1 is less than z2 in ascending order. So an element zi is compared with the element of zj, where I less than j if and only if one of them is chosen as a pivot. So out of this n element, if zi is chosen as a pivot, so zi will be compared to all elements of the array. Okay, and moreover, no two elements are ever compared twice. That means, so let's say this is a scenario you have. So you pick any pivot element from the set, and let's call that x, which belongs to zij from this set only. So from this set, so if you do that, then if that pivot element is chosen, then zi will come this side and zj will come this side. Okay, so basically what you're trying to say, if x is, first of all, if x is zi, then zi will be compared with all elements in the array, and if it is zj, then zj will be compared with all elements in the array. If x is zj, or if x is zi, then it will be compared with all elements in the array. But if x is in between zi and zj, then there is a problem. Then none of the element, I mean, then zi and zj won't be compared. Okay, this is the important thing. So what happens here, what it is trying to say is that moreover no two elements are ever compared. So so if X belongs to 𝐳𝐽𝐼 is chosen as a pivot during the execution of the algorithm, there are three cases to consider. First case is that X is neither 𝐳 nor X is neither 𝐳𝑖 nor 𝐳𝑗. That is, X is in between. Then 𝐳𝑖 and 𝐳𝑗 won't be compared because 𝐳𝑖 is the ith smallest element and 𝐳𝑗 is the jth smallest element, and they all are in ascending order. It could be the scenario that X is not 𝐳𝑖, X is not 𝐳𝑗. It is in between. Then problem happens. Then 𝐳𝑖 and 𝐳𝑗 won't be compared. So if let's say this is the X here, so 𝐳𝑗 is this side, 𝐳𝑖 is this side, and 𝐳𝑗 is this side. They won't be compared. This is one thing. Second thing is that if X is 𝐳𝑗, then obviously if X is 𝐳𝑖, then obviously 𝐳𝑖 will be compared with all the elements in the array, Z1, Z2, Z3, Z4, like that. In fact, 𝐳𝑖 will be compared with 𝐳𝑗 also in the first case. And if X is 𝑧j, which is the jth smallest element, then also 𝐳𝑖 and 𝑧j will be compared. So if it is 𝑧i, if X is 𝑧i, then 𝑧i will be compared with 𝑧j. Okay, so expected comparison, probability of comparison will be 1 when X equal to 𝑧j. When X equal to 𝑧i, then also probability will be 1 that they will be compared to each other. But if they are in between, then there is no chance. Then 𝑧i and 𝑧j will be compared in any time. Okay, so these three cases arises. Now, as an example of the lemma, consider the input. So let's say this is the array and 7 is the pivot element. 7 goes here, and then all the elements which are less than 7 comes here, and all the element which is greater than 7 comes here, and thereafter this pivot from this side and pivot from this side won't be compared to each other. Okay, so you see the values Z7 and 9 are compared because, so 7 will be compared with 1, 2, 3, 4, 5, 6. I mean 7 also will be compared with 8, 9, 10. But then thereafter, because these two sub-arrays that has been partitioned from this original array, so pivot element from this side and pivot element from this side won't be compared in future, because this will be having its own path and this will also be having its own future path. So no comparison among these two sets, because this is also a set, this is also a set. So what it says, the value, so first of all this is then the value 7 and 9 are compared because 7 is the first item from Z7, 9, which is true. Z7, 9, 7 is the first element chosen. In contrast, 2 and 9 are never compared because the first pivot element chosen from 2 and 9 is 7. So if 2 and 9 will never compare, because first if it is Zi and so 2 and 9 are never compared because first pivot element is chosen from 2 and 9 is 7, and this is in between 2 and 9. So 2 and 9 won't be compared. Okay, this is what it says. If X is in between, then problem happens. Otherwise, if X is Zi, then fine. X is Zj, then also fine. Then they will be comparable. The probability of comparison will be 1. Okay, so this is done. So next is what? So based on that, we have another lemma, which is lemma 7.3. Consider an execution of the procedure randomized quick sort of an array of n distinct element Z1, Z2, Zn, which we just discussed, given two arbitrary elements Zi and Zj, where I less than j, the probability that they are compared is 2 by j minus 1 plus 1. Okay, now let's look at this scenario, how this is very important. Let's look at the tree recursion call that randomized quick sort makes, and consider the set element provided as input to each call. Initially, the root set contains all the elements of Z I j. Since the root set contains every element in a, the elements belong to Z I j all stay together. So what they're trying to say is that all stay together. That means initially this is the scenario, this is my Zij, so everybody stay together, everybody stay together initially. Okay, so Zij all stay together for each recursive call of the randomized quick sort and partition chooses some element x belongs to Zij as a pivot. From that point on, the pivot x appears in two subsequent input sets. The first time that randomized select chooses a pivot x belongs to Zij from a set containing all elements Zij. Each element in Zij equally likely to be x because the pivot is chosen uniformly at random. Since the modulo of Zij equal to j minus I plus 1, that is the number of elements participating in the array, the probability is 1 by j minus I plus 1. What they are trying to say, so first thing first, here let's say this is my Zij initially, and how many elements are there? 10 elements. So what is the probability that any item can be picked? Any item can be picked, it is, and that is Zi. Any item can be picked, that is Zi, which is 1 by 10. And this is the one thing. Another thing, another important thing is that expected value of xij equal to 1 into probability plus 0 into 1 minus probability. Okay, so this is ultimately expected value of xij is equal to 1 into pij. Okay, so that is the probability that whether zi and zj will be compared or not, right? So here let us come back again. So probability that zi is compared with zj equal to probability zi or zj is the first pivot chosen from Zij. If it is the case, that is the probability, which is equal to Zi is the first pivot to be chosen from Zij plus Zi is the first pivot chosen from Zij. Zj is the first pivot chosen from Zij. That means what is the probability of choosing Zi here, which is 1 by 10. Okay, and what is the probability that Zj will be chosen? That is also 1 by 10. So basically this is total probability is 1 by 10 plus 1 by 10, which is 2 by 10, which is 1 by 5. So what does it mean? Meaning is that so Zi is the ith smallest element. Okay, Zi is the ith smallest element and Zj is the jth smallest element, and the subset Z, the subset stays together in the algorithm until some pivot in the range of Zi to Zj is chosen. Okay, so what is the probability? So first thing is that either the as it is written here that that Zi is the first pivot will be chosen or Zj will be chosen. These two probability, actually Zi will be chosen is 1 by 10 if 10 elements are there. Zi is the pivot to be chosen, and Zj will be chosen, that also is 1 by 10. But what if it is in between Zi and Zj? Then let's say it is not get chosen. Any pivot element between Zi and Zj is not got chosen. But then somewhere down the line in the tree, until they stays together, that is fine. But somewhere down the line, that range has to be splitted by choosing one element from Zi to Zj. When that is happening, then Zi also has the chance of getting chosen, and Zj also has the chance of being chosen as a pivot element. That's why it is 1 by 10 plus 1 by 10. Okay, so 1 by probability that Zi will be the first pivot or plus probability of Zj is the first pivot. That means even if they stays together, Zi and Zj, let's say x, the pivot that we are choosing is not Zi, neither it is Zj. That means the pivot is in between. Okay, the unknown thing. But that will happen until unless Zi and Zj, the pivot is until unless they are staying together, but somewhere down the line in the tree, the pivot will be in between Zi and Zj. So that split will happen sometimes. When the split will happen, Zi also has the probability of getting chosen, and Zj also has the probability of equally being chosen from that. So that is 1 by j minus 1 plus 1 plus 1 by j minus 1 plus 1. Both has the equal probability. So that will be the case. Okay, so it is totally 2 by j minus 1 plus 1, because j minus I plus 1, because j minus I plus 1 is nothing but the number of elements. Okay, so if it is the case, then we have, based on that, we have the fourth lemma, which is the expected running time of randomized quick sort on an input of n distinct element is O n log n. Now here also similarly we have Z1 less than Z2, which is in ascending order, and variable xi equal to I, that means they will be compared if Zi is compared with Zj. So whenever there is a comparison, the probability of comparison is 1. If Zi is chosen as a pivot, then Zi and Zj will be compared, probability is 1. If Zj is chosen as a pivot, probability of comparison is again 1. But what happens if it is in between Zi and Zj, until unless they stays together, it is fine. But once, I mean, somewhere down the line it has to be getting splitted. That time, what is the expectation? Expectation will be nothing but the probability, that is 2 by j minus 1 plus 1. So and we take expectation both sides, expectation of x and expectation of this expression, which is nothing but a mathematically if you solve it, you will get the final. So this is expected value of 𝐿𝑖𝑗, and the probability, that is nothing but probability that Zi is compared to Zj. This is from lemma. So this is very simple, and then finally you are getting, we are replacing this probability just now we calculated, which is nothing but 2 by that Zi will be compared to Zj, which is nothing but 2 by j minus 1 plus 1. So if it comes here, then finally if you solve it, so if you solve it, then it will be O n log n. This is for you to do. This is very simple mathematical calculation. Finally you get O of n log n. Okay, so basically, so this is the final conclusion, that expected running time of randomized quick sort is big O of n log n.